Okay, so my name is Graham Hay. I'm now at Morgan Stanley. I was at Credit Suisse last time you saw me at the spring event when we were doing the town hall. It's great, I must say, great to see Morgan Stanley sponsoring this, and it's also great to be part of that organisation that helps sustain the ONUG effort. So it's my honour to introduce this session. The standing joke would be that this is the session between you and cocktails, but you do not want to be looking forward to cocktails. This great debate is always a fantastic part of the programme that you should be looking forward to. So I'm not going to blather on any more about that because you want to hear from our folks here. So running the session today is Ernest Leffner, a newcomer to ONUG, for those of you who don't know him. Not at all. He's been running the great debate for many years. He's the co-founder and co-chair of ONUG. In his day job, Ernest is SVP of Infrastructure Solutions at Bank of America, running engineering for Bank of America's global network and infrastructure solutions. It says here he's an invaluable contributor to our ONUG community. Okay, that's fine. I have to read what's on here. So, and our guest today, so we have Dr. Douglas Comer, who's a distinguished professor of computer science at Purdue University. He's going to take the pro-hardware position in today's debate. We have Dr. Brighten Godfrey, who's the Associate Professor in the Department of Computer Science at the University of Illinois at Urbana-Champaign, and he's going to make the argument in favour of software. Will software make everything better? Over to you, gentlemen.
The question posed to us is, will software solve networking's biggest problems? So what I'd like to actually start with is the question of, what are networking's biggest problems? What are the grand challenges in networking? I went actually through kind of a midlife crisis. Okay, a couple decades early. But while I was in grad school, trying to get more excited about networking, I wanted big challenges. I was looking at, if you look at other fields, there's these crisp grand challenges like understanding high temperature superconductors in physics, or building practical electric vehicles, or in computer science, resolving the question of whether P equals NP. So it didn't seem that in networking and in systems we had those crisply defined grand challenges. What is the P versus NP of networking? So I informally surveyed a bunch of colleagues and researchers, and got a few different kinds of answers. About a third of the responses, well, the grand challenge is whatever I'm working on, obviously. Okay. A third named kind of vague areas where we need improvement, but without that crisp statement of a problem. Security, reliability, usability were the top three at that time. And about a third of the respondents said, well, there isn't really a crisp grand challenge for networking because it's infrastructure, and it needs to support diverse requirements, both across space and across time. And I think that actually points to a challenge of, that's kind of a meta challenge, if you will, of evolvability. How do we build infrastructure that can adapt and change to new environments? Okay, but this was 6-7 years ago, and it was kind of broad networking. Now we're in the specific context of enterprise networking with the benefit of more experience. And to learn about the challenges in that context, I think we could look at the working groups that have been identified by ONUG. And just very broadly, we can overgeneralize these into a few categories of challenges. There's work on virtualization, on visibility across different kinds of infrastructure and bringing that information together and extracting the meaning from it. There's work on security, and there's work on automation. So let's talk about each one of these and think about how we're going to solve these challenges. Are we going to be able to solve them through open APIs, through software, through SDN? Okay? So first, virtualization. Well, virtualization of networking is kind of explicitly about softening the hardware, turning hardware into software as much as possible. And I think to do that, we do in fact need open APIs so that we have a definition of what the hardware is, and we can virtualize that, we can emulate it. And we have progress in that direction. Visibility, let's move on to that. Okay, so I think an interesting thread that's come out in the presentations, discussions here yesterday and in recent meetings is we need visibility that's not just one little piece of equipment, but synthesizing information across layers, across components. And this is kind of a classic big data problem. We're bringing together different kinds, heterogeneous sources of information from different systems. Not only networking, but compute and storage, and analyzing it in new ways. And really the only way we know how to solve that is through software. Okay? Now let's go to security. I think a common thread that was, not to totally overgeneralize, but in the security working group, one common thread I think is that we need to understand what the applications are, and their associated trust needs are, right? So we need to understand applications. We need to be able to move with applications wherever they are. And so if we have to keep up with software applications, I would posit that we need security really to be as agile as software. It needs to be software. And finally, automation, and this is getting at one of the key potentials of software. Right? So if we think about the history of networking, we're in the place we are because the architectures that have gotten us to this point, network and internet architecture, was built in a simpler time. Right? A time when networks had simpler functions of data delivery. But now we have much more complex requirements, and so networks have themselves gotten more complex. And normally these networks are proprietary, but I was actually able to get video footage of packets as they're being delivered in a modern enterprise network, and it looks like this. Let you just enjoy that. So in a modern network, there are a lot of moving parts, right? And those moving parts and systems of systems need to be orchestrated. And so lacking APIs in the past, lacking the human resources to program that infrastructure, we've come up with processes that exist at the human level, right? Change management. And the problem here is that they operate at human timescales and might involve tens, even 100 people involved in making a change to a network, let's say. So we need to be able to automate that and turn those human processes into software, right? And there's a big opportunity there. Okay, so walking through each of these challenges, my conclusion is that really software is our only hope at addressing the biggest challenges. So it better work. And I think the good news is that we are actually seeing some success. And I will mention two examples, which are probably familiar to most of us. And the first is in software-defined data centers, both in the Facebooks and Googles of the world, and also in products that are helping companies build private clouds. These have been a virtualization win. That's something we could not have done without APIs and software. An automation win, for example, Facebook being able to support 20,000 servers with, per engineer, roughly 2 orders of magnitude more efficient in terms of human resources than in traditional IT. And I'd argue it's actually an evolvability win. Now, why is it an evolvability win? One of the key needs that drove us to software-defined data centers and virtualization specifically is to be able to take existing applications that depend on certain properties of layer 2 or multicast or addressing and bring them over to a new infrastructure. So in a sense, and yes, in a scoped environment, it's actually helping us evolve the infrastructure to a very different architecture than some of these applications were designed for. And second, in WAN traffic engineering. So both Google and Microsoft have described how they've been able to get very efficient wide area infrastructure, driving that to 100% utilization with 0% packet loss on traffic that needs 0% packet loss. Efficiency win, an automation win, and a visibility win, because to make that happen, they are synthesizing information about applications. They can see what applications are across multiple data centers, where they are, and what their performance needs are, and affecting that in the network. Okay. At the same time, there are open questions that we can discuss, so this might seed some of the discussions. First is teasing out what are the killer apps. Okay? What I just described are some wins, but they're scoped wins. And if we think about the broader enterprise infrastructure, there's much broader needs. I don't think we're going to have a single SDN controller that solves every problem, or even a single SDN programming language that solves every problem. Second is reliability. Software may be less reliable, but I think here we're going to actually end up with another win, because we're going to have much easier testing and verification, even potentially mathematical verification of some of these systems if there's defined APIs. And we will need to define what those APIs are for monitoring, control, policy, and orchestration. And that's getting at questions of performance. And I think the question we're going to arrive at there is, what is going to be the boundary between software and hardware? And how little hardware can we get away with? So, takeaways. I think our only hope is a software-defined world. Fortunately, we know, by example, that that future can be brighter. There's light there. And a particularly interesting question that we'll discuss, I think, over perhaps today, but also in the coming years, is how narrow of a role for hardware can we get away with?
Here's the problem. Software is bug-ridden. You remember last summer. How's software been working for us? Do you remember the newspaper headlines? They all said, are we under a cyber terrorist attack? Is the world going to fall apart? And a couple days later, guess what? They ran the true story. Oh no, it's not a cyber terrorist attack. Don't worry. It's just regular old software bugs. Really? Don't you remember that? But software is dangerous. You know, we know all the annoying, inconvenient, time-consuming, but guess what? Software can take human lives. Software engineering. When I was out in Silicon Valley, I was working for Cisco. They sent me to a meeting with a whole bunch of other companies. And one of the interesting things that happened was inside Cisco, people repeated a little mantra to me that I didn't quite believe. But we got to this meeting and the guy on stage said it point blank. He said, one outstanding hardware engineer can do the work of 2 mediocre hardware engineers. One outstanding software engineer can do the work of 20 mediocre software engineers. The guy standing next to me looked at me and said, that's not true. It should be 12. So I asked myself, what's going on here? Is software really more intellectually challenging than hardware? Is that really what's going on? Or maybe universities aren't preparing software engineers the way they prepare hardware engineers. Now I point to my opponent who teaches in a university. I think everybody who teaches software engineering in a university ought to... Oh wait, forget it. Okay, let's look at the legalities of things. If you build a product in this country, you have product liability, which is why we have all those recalls for cars, because they have to work the way the manufacturer claims they work. But guess what? Software, the whole legal system says, oh, we know that's not going to work. So all you have to do is put this little label on as is, and you have no liability. We admit it. The legal system admits that software is so hard that they can't enforce liability. You got to think about that. Software always degrades. You know what happens. It starts out good, you get version 1, it seems to work, we get all of this demand, and then success attracts a whole bunch of wannabes who come along and they work on an already bloated version of the second generation, and it's terrible. So each successive generation is worse. You know that, right? It's true. Everybody admits it. You remember Fred Brooks' warning? You don't remember Fred Brooks? Here we're talking about software engineering and you don't know Fred Brooks. You got to go read it. He warns about the second system syndrome. But it's not just Fred. I was talking to a guy in Silicon Valley who manages software engineers, and he said, I've managed hardware engineers, I've managed software engineers. Hardware engineers have an advantage. They can tell you when something is done. Software engineers, they're never done. They always want to add one more feature or one more modification or one more parameter. Right? You may have seen Douglas Adams' statement. Normal people believe if it ain't broke, don't fix it. Software engineers believe if it ain't broke, it doesn't have enough features. So it's always easy to add features to software, and that's the problem. And now, after all of that, after we know about software, they have told us if we put more software in the network, it's going to make things better. Haven't they been paying attention? We know what's going to happen. Put more software in the network and you'll see the headlines, just like at the beginning. The network is broken. Oh, what are we going to do? So I ask you, why would anyone rush to put software in a network? Does this make any sense at all? Haven't you been paying attention? Are we crazy? So the summary, software is fraught with peril. We'll have problems, problems, problems. How can you think software will help? Everyone's gone crazy. All right. Actually, before I leave I know that a lot of you are addicted, but I want you to say something for me. Just help me out here. Repeat after me. Just say no. Ready? Just say no. Great. Thank you.
Thank you, Brighton. Doug, that was absolutely informative and entertaining. Though I think we should talk about hardware problems that have cost lives too. And I don't know about you guys, but I just need one more hit. Just one more hit of software, and that's going to make everything better. I don't know if I can say no quite yet. So, as this is the great debate, we like to drive these questions, and we really appreciate audience participation. So, I have a few questions that are queued up, but I would absolutely invite folks, head up to a microphone right now, and let's start asking some questions. So let's start driving this debate, right? In the end, you've got Brighton, who I think very clearly articulated that he believes software is the only way forward, right? And we've got Doug, who I think has made a very good case on why would we ever put another piece of software, sort of in the network again. And I'm sure we've got a lot of bright folks in here that have opinions on this that we can drive questions. Anyone want to step up to the bar first, or shall I ask to lead it? Come right up to the...
I'm an old hardware engineer, so
Could you sit back down again then? I'm sorry.
the operative word being old. But I'm gonna make a point about software I think needs to be addressed. I think our culture has adopted this, as is notion for software because it it has been sloppy. And the best software engineers I've run into are actually old hardware engineers as well. And it's because there's a right way of engineering things, and software to this point has not been very well engineered. And I think a lot of these headlines we see are basically just excuses. People saying, oh, it's a software problem, when in reality some bonehead probably did something stupid.
Clearly you agree with Doug.
I actually agree with both of them, of course, but I think software has just been sloppy, and that's the problem. It has not been engineered, it's been slapped together. So maybe some commentary from both on that.
Sure, yeah. So I think what that's illustrating is that software doesn't have to be buggy. It's about the processes and care that we put into it. And if we're thinking about software as critical infrastructure, then we can build reliable software, right? I mean, in fact, to flip it around, hardware is in a sense just software too. We're designing algorithms and circuits. It's code, right? It's all code in a sense, except that the mentality when we're building hardware is that we better get it right because it's going to be, burned onto a chip. Now we better get it right because it's critical infrastructure. It's in the network, right? And so we will have to get to that point where the processes are in place to, so that is actually realized.
Yeah, so my take on it is if you go look at the way we teach hardware engineering, one of the things that seems incredibly constraining to a computer scientist is there are all these design rules. You could hook it up 17 different ways, but the design rules say do it this way. And if you take two hardware engineers, you give them a problem, chances are very high that they will come up with almost the same design, modulo some minor differences. You give two computer science students, graduates, a problem to program, and they will come up with 4 different designs. And they'll all be different. I mean, it's just amazing to see the uniformity in hardware. That makes hardware engineers much more replaceable. It means that everybody can understand what the guy did because that design is the same design I would do as a hardware engineer. So I can see, here's how it should work, and yeah, I can understand it. But you give software to people who haven't designed it, and they look at it and they're amazed. How did they ever structure this? I mean, I've heard so many people say that. Look at the structure of this, how did it happen? I think we're really missing something in the software world. We've been wide open, encouraging people to try 1,000 different things, and we should be encouraging them, just like the hardware engineers, to stick to tried and true design rules.
Hi there. So I manage an infrastructure team, but we've been using a lot of software processes like Agile, Scrum, that sort of thing. And it draws heavily also on lean manufacturing concepts. So we've seen value in both worlds in terms of our own processes and deploying things. So maybe you guys could comment on the role of Agile, lean, and the whole movement to that in terms of deployments and projects, and if that has a useful role here to help with the situation.
Sure, I'll begin. So one of the main things that people told me when Agile came out is we're going to lower costs. It's going to be really fast, and I pointed out that means we're going to have software that's quick, flexible, and fast. It doesn't really help much to talk about a new paradigm for, a new programming language or a new programming paradigm. There's a new one every 4 or 5 years. The software engineering community keeps churning out yet another paradigm. And of course, everyone has its advocates, and because it's brand new, all the programmers are saying, I get to do something new. I'm going to try hard to do this. And it works. And the next one works. And it works for a short time, and then pretty soon, they're not trying hard anymore, and there's no magic that you can say, if you follow this, it's definitely going to be the thing. So what happens is we just go from one to another, And we're not really making forward progress. Sorry, but I just don't think that whatever the flavor of the day is, whether it's Agile or DevOps or anything at all, is ever going to be the solution.
So I actually agree with Doug, but I think
Remember that when you vote.
But I think we're kind of asking the wrong question in a sense, because in many cases we're not replacing hardware with software. By moving towards open APIs and SDN in a more programmable world, what are we replacing? Well, we've had to get a lot of these tasks done before. We've had to provision networks. We've had to implement security controls. We've had to optimize routing. But all of that, all of those algorithms were algorithms implemented by humans, right? So if you look at the processes like on that Cisco best practice flowchart that I flashed on the screen, which is itself a very high-level summary. That's like a algorithm that's coded out that the collection of diverse and sometimes inaccurate, often inaccurate, always inaccurate humans are executing, right? What we'd like to do, the opportunity here is taking that sort of software that's executed by humans and executing it with microprocessors instead, right? And if we do that, then there are some magic opportunities, since you used the word magic, right? The immediate win is, of course, in automation, right? But in terms of reliability, we can take ideas from hardware design. In hardware, you do verification of chips, right? We can do testing, we can do unit testing of software. You can test your controllers in advance. This was one of the drivers for Google to adopt SDN early on, was to be able to emulate an infrastructure and test changes to control software in advance of deploying. So there are some of those processes that could result in big wins. Now, is that agile? I don't think that's going to get us to high reliability, and it may in fact let us move much more quickly and innovate faster. But it's got to be balanced with if we're working in the network, we're working on critical infrastructure, we've got to have the processes in place so that we build reliable software in the end. But I think the exciting thing is that there are those threads of possibility there so that we can realize it.
An optimist.
All right, next question.
Yeah, so when we think of software, especially networking, right, I think the joke is automation is misconfiguration at scale. So, that's low-hanging fruit, right? It's easy to point at those things and look at these failures that were brought up. But I think on the software side, you get to just kind of roll that back. In my experience, I've actually seen hardware issues at manufacturer that are only exposed after like power cycle 10,000 on 500, around 5% of all nodes. Huge issue. But now all this stuff is out in the field. You do a fleet-wide upgrade in your data center, you reload all these boxes, and 70% of your line cards don't come back. Now your solution for that has to be physical replacement versus, git revert. Comments from either side on kind of, hardware has validation, but when that validation fails, it's way worse, it seems.
So thank you for okay, so right, so there are big concerns with hardware, and you articulated one, and I don't have to respond, I just have to take sort of make an extension of your point there, that what could be even worse is intentionally introduced flaws into the hardware, right? So imagine that your supply chain is compromised, and your parts are manufactured for every machine we're using is an international project. If there are intentional flaws, backdoors introduced into that hardware. Now that's a really scary scenario. At least software, we can fix it.
First of all, let's look at history. How many software upgrades have caused problems compared to hardware failures after 10,000 reboots? Yeah, everything fails. Let's face it, there's nothing that's perfect. But, and power supplies fail and hardware has to be replaced, that's true. But look at software. Look at how much trouble we've had with crazy software things going wrong compared to hardware things. You have to just step back and ask yourself statistically, what do I want to bet on? I want to bet on hardware, and I'll bet you do too.
So this is a comment more on the software side, and I think we are ignoring certain very, very basic points, which is over the years, software has enabled a lot more things than hardware would even try to achieve. I mean, if we might still be in an ENIAC phase if we just did hardware from 1950s, right? The fact that we have a computer right now, the fact that we have a mobile phone, and the fact that we are able to do a lot of things, right? And so that's one data point. Second data point, the number of EE students that I've interacted with who want to do software is way higher than the number of CS students who ever want to do hardware. Just those 2 points.
Yeah, I understand that completely. The EE students come over to computer science, where I'm a computer scientist, and almost inevitably one of them will say, this is so much easier than that stuff. As long as you don't have to get it right.
Well,
It's okay, you can agree.
we do have to get it right, but you know, we don't have any choice, right? So if we want to, you know, we could stick with, you know, the ENIAC, right? Or we could capitalize on, you know, a huge array of exciting opportunities and innovation, right? And so I think what this, you know, the reliability and bug discussion is pointing to is that we're going to be forced down the path of building systems with software. There's no other way that you can orchestrate a large, complex system of systems but by understanding it with software and ideally with APIs so we can pull out the data, right? So,
So you're
we don't have a
saying-
choice.
So you're saying that you really wouldn't choose software except we're being forced.
Next question. Yeah, I'm just curious if you could comment a little bit about, you know, you can write, you know, ASICs and things. You can put what could be in software into hardware with the argument that it can be made more efficient, be super optimized. Even some software you can put in a register variable, whatever. So where do you draw that line? Is there some formula that says, yes, hardware can always do this much more efficient if coded exactly to a hardware routine, and that's where you say, if that's the performance, the efficiency you need, that's where hardware has a play, and then if you just need more general, you know, less performance, whatever, because you still see a lot of companies saying, yeah, I'm going to spin ASICs forever, you know, the F5s, et cetera, yeah, I'm still going to be in the hardware business, Cisco, so it seems like people are saying there's still a line where hardware is the right way to deliver a feature.
Hardware is definitely the performance winner. As long as you have a fetch execute cycle in there, software will be slower. So we know that, and if you want really high performance, you have to go to hardware. So that's an easy point from my side. Sorry.
Well, I'm going to actually argue that software gets us better performance. Okay. So now, clearly, we need hardware to run software. right? This is undeniable. And actually, it's a fascinating question of where is that line and what are the APIs? What components do we need to, functions do we need to hardwareize? And there's a lot of interesting work here with FPGAs, or we could also look at like the P4 language for building custom pipelines and switches, which is in a sense taking something away from the hardware, because now the software is defining even some of the hardware structures that were there before. So that's a fascinating line, and actually I think the project there is, the mindset that we're moving to is not, do we put more in software? It's how little hardware can we get away with, right? And so that's illustrative of the fact that we're, of course we'll always be running physical hardware, but we are simplifying it and giving it as limited a role as we can. And that's healthy because it's allowing us to innovate and build better systems, right? And systems that can be, structured and use modular design and good software engineering practice. But how are we going to get even better performance from software? Well, performance now means more than just like line speed on a box, right? We've got to understand the full picture. We need to, imagine you want to do quality of service. This is something you've got to understand where your applications are, the end-to-end behavior, real-time congestion maybe in multiple places, and the needs of end users, and bring that into a cohesive whole that lets you optimize the whole system. And if you want that whole system view, which is what today we need, the whole system application-oriented view to get good performance, that's going to be software, right? And this is how Google and Microsoft have optimized their WANs, is through those kinds of processes. So I would argue that in the future of performance in broader systems is actually software.
Yeah, I wanted to say that your point, Brighten, before about that we're not considering in this debate humans, because when we're looking at a lot of the automation and software-defined infrastructure concepts, a lot of it is about automating what humans previously did, whether it was respond to an attack or automating the provisioning process, things like that. But I think, Doug, you made a good point, software has bugs. So where is that balance of automating by still having the human in the loop? Do you completely eliminate the human, or are there certain points, given where today's technologies are, that you sort of say, okay, listen, I don't want buggy software there. The implications of a bug in my software with that function are too serious for me to automate that particular network operation function.
Well, I would say that humans have even more bugs than software, right? So if we, the cool opportunity here is we can make this infrastructure, which was closed before and siloed, into something that we can build with not slipshod software engineering practice, but good software engineering practice. We can make it modular, we can make it documented, we can test and verify, and get to that place where it'll be better than what we have now.
Speaking to a whole room of network managers, I want to tell you that people are much better than software.
We could vote on that.
So we're right up against the 4 o'clock. I think I'd like to take, do we have time for just one more question, Nick?
Yeah, and vote too.
Yep, so please, while we're asking this question, hit your cell phones, please, and vote. This is an important vote. So one more question, thank you.
Thank you very much. I've had the great pleasure of being both sides of this, been both hardware and software and along the lines. By the way, I've fixed enough chip erratas in software to, frankly, write a long story on there. But the fact is hardware won, and we're living in a software world because hardware won. It's only because the tremendous capacity that hardware has provided us to have algorithms and software at real-time networking infrastructure layer that software is capable of doing what it's doing now. But I think the one thing I don't hear us talk enough about here is creativity and the ability to adapt to the user needs immediately as they come up. Hardware costs $3 to $6 million to spin a chip. Software is the dip that goes with the chip, but I don't think we're going to have a lot of creativity if we have to spend $3 to $6 million every time we want to actually do something new. So could you please address that? Thank you.
Oh, it's true. With software, you get the ability to create new things, lots of flexibility, make things quickly and try new things, and you can make software that fails really fast.
Well, I think this is about evolvability. We have to change, and it's an exciting time we're in because there is major change in infrastructure now, and that's going to happen fastest by defining a very clean set of hardware that'll let the software run quickly and evolve. So I think that's the boundary. That's what is that API to the hardware that we're talking about?
I don't want fast, I want good.
I think we can get fast and good with the help of the hardware. I am an optimist.
You are an optimist.
Yes.
All right, first off, let's give a big round of applause to our debaters. As always, this has been, I think, one of the best debates we've had, right? And the candor, and I think the humor that went along with the back and forth was very, very well received. But, in the end, this is a topic that's near and dear to every one of our hearts, right? It's something that we deal with every single procurement cycle that we go through, every time we look at a new technology innovation. And we're not doing ourselves justice if we don't try to understand both sides of that equation, right? And really understand where the problems lay. So ultimately, thank you both again. Right now, you're 50-50. Well, 49-51 for Dr. Godfrey.
Oh, no.
Any last minute votes?
This is like the Florida recount.